I'm going to be starting off the presentation today, but first we're just talking about carbon capture and sequestration. That's our topic that we had, and I guess next slide. All right, so before I start my thing about carbon capture, I just want to talk about some basic things. So carbon capture and sequestration involves the capture of CO2 from power plants and industrial processes, the transport of the captured CO2, geological sequestration, which is storage of the CO2 underground or released into the deep ocean, capturing and storing carbon and organic material and vegetation as well. And the overall goal is to reduce CO2 greenhouse gas emissions from industrial sources and mitigate global warming or climate change. All right, next slide. All right, so I'm going to talk about the carbon capture technologies. So there are three types of carbon capture technologies. The first one is pre-combustion, and this is when the CO2 is removed before it's combusted, as you can tell by the name. So this involves fuel being reacted with steam and oxygen under pressure and high temperatures to form a synthesis gas or a syngas of mostly hydrogen and carbon monoxide. This hydrogen gas can be used to power a turbine in a power plant by being burned to power a boiler, which turns a turbine. It can be used for other things too, like fuel cells. So then the carbon monoxide reacts with water to make CO2, which can then be removed. And that's what to say. This usually takes place at an integrated gasification combined cycle power plant, or an IGCC. That's usually used for coal too. But in general, this technology too is, like I said, mainly used for coal, but to a lesser extent for natural gas. And it makes use of physical absorption, which is usually like absorbing something with a solvent, or adsorption, which is like when it's a thin film is formed over the absorbent. Next slide. And before I actually go back, I just wanted to point out right there on the right is a diagram of a pre-combustion machine. So, all right, next slide. Yeah, there we go. So the second type of technology is post-combustion carbon capture. And this is, as you can tell by the name, when the CO2 is removed after combustion. And it usually involves CO2 being separated from flue gases, usually using a chemical solvent like an amine. The most common amine that's used is called monoethanol amine, or MEA. And how this starts is flue gas is cooled to around 40 to 60 degrees Celsius and put in the absorber where the solvent absorbs CO2. Then the solvent is heated in what's called a stripper at 100 to 140 degrees Celsius, where the CO2 is condensed and removed from the solvent. Also, membranes have been used to separate the CO2 from the flue gas, and cryogenic separation has been used in place of amine scrubbing, which is what I described before. And cryogenic separation is basically when, excuse me one second, the flue gas is cooled until the gases liquefy, and then the gases are distilled and removed based on their boiling points. And that's how they remove the CO2, is they remove it when it's boiled. So, all right, next slide. And there's a diagram right there. The third type of carbon capture technology is oxy-fuel combustion. And it's usually burned in the it involves fuel being burned in the presence of pure or enriched oxygen, causing the flue gas to be mostly carbon dioxide and water. How this starts is an air separation unit is used to create the pure oxygen by separating it from nitrogen and other gases. Usually, I think one of the most common techniques for separating the air was cryogenic distillation, which is what I described with cryogenic separation. And so what this involves is like it's burned, and then at a power plant, it usually powers a boiler, which creates steam to turn a turbine. Um, During this whole process, too, some of the flue gas has to be recycled and burned to control the temperature of the boiler. That's one of the problems with it. And the flue gas, when this is all done, the flue gas is compressed and cooled to remove the water vapor, leaving behind pure CO2, which can then be removed. All right, next slide. All right, so some industries that use this technology are all forms of power plants use this technology, as I described before, like an IGCC plant, as an example. Also, one of the big industries that uses this is the cement industry, and they've used various forms of oxy-fuel combustion. They've also used post-combustion, usually amine scrubbing, and they've used what's called calcium looping, which is a post-combustion technique. And calcium looping is where a metal is reversibly reacted between its carbonate form and its oxide form to separate carbon dioxide from other gases. And a reversible reaction would be where like the products and reactants and products to reactants are occurring simultaneously. Another industry that uses this technology is the steel and iron industry. They usually use like gas to liquid absorption or calcium looping. And they also pre-combustion and post-combustion has been used in the oil and gas industry. Usually it's amine scrubbing. An example of that would be amine scrubbing and membrane separation being used in natural gas processing. So, and over here on the right, there's a table showing some of the biggest emitters of CO2. And you can see right there, power is the largest in terms of like total emissions, then cement, iron and steel, refinery and oil and gas and all that. All right, next slide. So some of the costs associated with this technology are, most of the technology for carbon capture is pretty expensive to implement and use at the moment. For example, MEA solvent, which I mentioned before, is very expensive for post-combustion carbon capture. And gasification at an IGCC power plant is expensive to implement. And I'm not sure if I mentioned this, but gasification is what I described when with the hydrogen and carbon monoxide and all that. So this technology also, another cost is that the technology has an energy penalty. And an energy penalty is basically, sorry, give me a second. Energy penalty is defined as the reduction in the net electrical energy from a power plant caused by the addition of carbon capture, or the increase in the required fuel for our power plant to maintain its power input after the addition of carbon capture. So basically, they have to burn more fuel to power the technology and maintain the power output for the plant, or if they don't do that, less power is produced, since the power produced by the fuel is being diverted for the technology. And then lastly, go back. I was going to say, lastly, electricity bills might increase because of how expensive carbon capture is to adopt and use, and also because of the energy penalty too, because they have to burn more fuel. All right, next slide. All right, some of the more environmentally focused costs are stored CO2 can leak out of the system and exacerbate climate change and can lead to acidification in water. Also, dust suspension and CO2 emissions during construction of the plants can also affect the air quality. And wastewater is produced by carbon capture, which can be harmful to the environment. As I mentioned before, chemicals such as like some of the solvents used can be pretty bad for the environment. All right, next slide. So I just want to end this on where some countries where the technology is in use. And most of the technology is in the United States. You can see on the total side here, 78% or 78 projects are in the United States. And but there's also it's pretty used a lot also in China, where there's 20 projects, Canada with 13, and Australia with 10. And there's, it's growing in other places too, like Brazil and Japan and the Netherlands too. So, and that's it for me.
Okay, can everyone hear me? Okay. So,
Yes.
I'm Cheyanne, by the way, and I'll be talking about how, whoops, hold on one second. Okay, I'll be talking about how the captured CO2 gets transported and what happens once it's stored. So after CO2 is captured, the goal is to contain the greenhouse gas and prevent it from escaping into the atmosphere. And by storing the trapped carbon dioxide or using it in industrial processes, the amount of CO2 emissions to the atmosphere could be reduced by about 80 to 90%. So CO2 is most often transported through pipelines, which can be underground or underwater, and they can extend from feet to miles beneath the surface. There are already over 4,500 miles of CO2 pipelines as part of the US infrastructure. And this map shows the major pipelines as black lines, and you can see that they're mostly concentrated in the southwest region of the country, but they're spread over more than 12 states and they extend all the way up to Canada as well. So the pipes start at the point of CO2 capture and they carry it all the way to the storage site. And sometimes the CO2 travels through the pipelines only until it reaches a tanker or a ship, which brings it to its final storage location. The pipelines transport CO2 as a gas. The pipes have compressors that keep it moving along until it reaches its destination. And in order to prevent corrosion of typical steel pipes, the carbon dioxide must be dry and free of hydrogen sulfide. Another option of transportation is by ship in its liquid state, which is used when it needs to travel over a longer distance or when shipping is a region's most practical option. CO2 can be stored and transported by ship as a liquid when it's contained under constant low pressure and low temperature conditions. And it can also be transported as a solid, which is known as dry ice, but this is more costly and much less common. Okay, next slide. So when CO2 reaches its destination, it's then injected underneath the land's surface and the pressure causes it to adopt a liquid-like form. And in this state, it's known as supercritical CO2. Sites of geological sequestration are deep, porous geological formations that the CO2 can seep into, like natural gas and oil reservoirs, coal beds that can't be mined, and saline aquifers. The process of geological sequestration is commonly used by oil and gas industries, since the injected carbon dioxide can push out all of the remaining oil and gas from the pores of the old reservoirs. Once the CO2 is injected, it's able to travel upward until it meets layers of impermeable rock near the surface that it can't pass through anymore. And this is known as structural storage, and it keeps the CO2 trapped under the Earth's surface. Mineral storage is another process that can occur during geological sequestration. The CO2 can chemically react with the surrounding rock to form new minerals, and the molecules are then trapped in the newly formed rock. Basalt, which is volcanic rock that makes up the ocean floor, is notably useful for storing CO2 because the carbon dioxide reacts with it to form limestone. Okay, next one. So another method used to permanently store carbon dioxide is releasing it to the bottom of the ocean at depths greater than 11,482 feet. With this method, the CO2 is liquefied under the high pressure and low temperatures in the deep ocean. And under these conditions, the CO2 reacts with water to form clathrate hydrate, which is an icy, slushy compound that sinks to the ocean floor and stays there. In this form, the CO2 will not be absorbed by the seawater because the nonpolar gas molecules get trapped inside cages of hydrogen-bonded water molecules. So this picture shows what the substance looks like. And the CO2 is the green molecules, and they're trapped inside the little hexagonal ice crystal cages formed between each of the water molecules. A 2018 study on the effectiveness of this deep sea method concluded that this process of hydrate formation effectively immobilized the injected CO2, which allowed them to conclude that it's an option of safe storage. The study explained that although it was possible for CO2 to diffuse into the surrounding water, there was no leakage because the hydrate film expands to trap the CO2. And in the long term, the CO2 eventually dissolves and is permanently stored in the deep ocean. So the goal of carbon sequestration in the oceans is to keep the dissolved CO2 away from the atmosphere and away from the upper ocean for longer periods of time, since it does the most damage in those locations because of global warming and ocean acidification. Next slide. All right, so while the storage of carbon is an important new method of reducing greenhouse gas emissions and preventing global warming, it also, of course, comes with risks. Since its techniques are new and developing, there's still little known about the dangers of sequestration and its long-term effectiveness. On land, little can be said about the long-term reliability of underground CO2 storage. There have been too few storage sites in existence for too short of a time to know how safe and secure underground pipelines and sequestration locations can be. However, the reliability of this process seems promising based on the Sleipner gas field in the North Sea, which has been storing CO2 efficiently for 10 years already without any leakage or complications so far. And in order to evaluate the potential risks of pipeline leaks, another 2008 study outlined how sublimation of dangerous CO2 gas could result during transportation through pipelines. The researchers explained that if a pipe leaked, the CO2 would create a bank of solid dry ice on the ground above it in response to the drastic temperature reduction once it reaches the surface. And as sublimation occurs, the gaseous CO2 would be released and it would stay close to the ground because it's denser than air. And this presents a concerning safety hazard since it would be an asphyxiant and it could cause circulatory failure, potentially leading to coma and death. And in the ocean, pipeline leaks would cause similar safety hazards because gaseous CO2 can cause major health complications. So for example, in 1986, a natural volcanic eruption occurred underneath a lake in Cameroon, and it caused a disastrous cloud of CO2 to explode from the lake, killing almost 2,000 people, thousands of livestock, and much of the lake's marine life. The gaseous CO2 acted as a severe asphyxiant, leading to the massive death toll that it caused. Although this was a natural disaster, it shows the potential devastation of a CO2 pipeline failure. Studies have shown that ocean storage of CO2 is effective for keeping CO2 out of the upper ocean and atmosphere, but the uncertainty of pipeline leaks and long-term CO2 concentrations still leave concern for ocean acidification. As CO2 is absorbed in the surface of oceans, it increases the water's acidity and harms the marine life living there. An important example is that it reduces the availability of calcium carbonate, which many organisms rely on for their shells. Next one. Thank you. Okay, so in 2018, researchers wanted to predict the potential of geological sequestration for CO2 storage security and leakage back into the atmosphere. They developed a storage security calculator to run their study, and it was based on the geological processes that would determine how well the CO2 could stay retained underground. And they also calculated the expected rates of leakage that would occur over time in different geological areas. They used these factors to predict storage security and leakage of the CO2 over a hypothetical 10,000 year period. They concluded that if storage facilities were well regulated and monitored, there would be a 50% chance that the leakage of CO2 into the atmosphere remains below 0.0008% per year. So obviously a very low percent chance. And they also said that over 98% of the injected CO2 would be retained in the subsurface over the 10,000 years. And they also concluded that in the unlikely case of inadequate regulation, more than 78% of the CO2 would still be retained underground. So this study suggests that geological sequestration seems to be a secure option for mitigating greenhouse gas emissions and climate change, but they also acknowledge that the long-term behavior of CO2 underground is still uncertain until CO2 storage is more widely used and studied. And that's all I have.
Hi, so I'll be talking about reforestation as one of the ways that we can eliminate some CO2 levels in the atmosphere. I do want to begin with some background. So carbon dioxide, so how does carbon dioxide cycle through plants and humans? So carbon dioxide is added to the atmosphere from many ways, like forest fires, burning fossil fuels, when organisms decompose, in many other ways. Another way is through cellular respiration when organisms breathe. The process of respiration produces energy for organisms by combining glucose with oxygen from the air. And during cellular respiration, glucose and oxygen are changed into energy and carbon dioxide, which organisms expel from their bodies. Therefore, carbon dioxide is released into the atmosphere and contribute to the buildup of CO2. The process of photosynthesis from plants is important in minimizing that buildup. In summary, you probably know what photosynthesis is and its processes, but it uses carbon dioxide and water from the air and soil. Goes through many reactions to produce oxygen and glucose. So both cellular respiration and photosynthesis are important parts of the carbon cycle, which are pathways through which carbon is recycled in the biosphere. They connect with one another where the exchange through carbon dioxide and oxygen through photosynthesis and cellular respiration helps keep atmospheric oxygen and carbon dioxide at stable levels. So here in this slide, you can see both equations of cellular respiration and photosynthesis, as well as their diagrams. Next slide. So what is forestation? So I want to start with talking about the opposite, deforestation. Deforestation is the removal of forests or trees from land that is converted to non-forest use. So throughout time, forests have been used to make space for agriculture and animal grazing, to obtain wood for fuel, construction, and manufacturing. Deforestation is the single largest source of land use related greenhouse gas, GSG, emissions, and accounts for about 10% of total current anthropogenic GSG emissions from all sources. This is a small amount compared to other factors that impact the climate, yet makes a big impact on our Earth with trapping heat and creating air pollution. In 2017, land use changes, mostly deforestation, contributed to 4 billion tons of CO2 emissions to the global total of 41 billion tons of CO2. So reforestation, also called afforestation, on the other hand, is the regrowing of forests that have previously been cut down using tree species that are native to the geographic area. So reforestation can occur naturally through germination or by human activity, by planting. I also have read that reforestation is often managed by lumber and paper industries in order to maximize the resources that make the continuation of wood industries possible. You might think that many paper industries are bad for the environment since they use trees for production, but from cutting trees for their use, they use forests as a crop in which trees are planted to replace those that have been cut. And they are, carefully managed by the industries. Next slide. So some benefits that come from reforestation. So one of the benefits, there are many benefits for reforestation. The first one would be having a genetic diversity of tree species that can lead to species diversity, like organisms, like insects and fungi, and also different animals. Also having a huge, habitats for animals, introducing other resources through these different species. But most importantly, they can act as carbon sinks. So from photosynthesis, U.S. forests alone can store up to 14% of all annual CO2 emissions from the national economy. And trees can lock up carbon in their wood and roots for decades or even centuries. Next slide. So some long-term effects of reforestation. So there are many sides that come into play with talking about how beneficial it can be. In the long term, trees can have a great effect in reducing CO2 in the atmosphere and slow down climate change, but it won't reverse it on its own. The rate at which carbon can be removed from the atmosphere through afforestation and reforestation is determined by a number of factors, which include the age of trees, species composition, temperature, and many other factors. Determining those factors could take a very long time and can become costly through the maintenance and research. And these factors can either help speed or slow down the CO2 intake. So some of the positive impacts that reforestation can bring is that there is an estimate that forests and other ecosystems could provide more than 1/3 of the total CO2 reductions required to keep the global warming below 2 Celsius through to 2030. This can reduce any risk that could become worse from having the atmosphere being too warm. And also a group of researchers claim that we can plant 1 trillion extra trees and remove 1/4 of the carbon dioxide currently in the air. Another good long-term impact is that forests can be an important stopgap while the world tackles the main source of carbon emissions, like burning fossil fuels, which is a huge part. And like I said before, it can slow down climate change, sequestering carbon dioxide from the atmosphere. On the other hand, there are some negative views on reforestation. Some scientists say that although trees cool the globe by taking up carbon through photosynthesis, they also emit a complex of different chemicals, some of which warm the planet. So, for example, the dark leaves of trees can also raise temperatures by absorbing sunlight. Also, several analyses in the past few years suggest that these warming effects from forests could also fully offset their cooling ability. So in conclusion, I've read that the benefits, it's more beneficial with reducing deforestation than that of reforestation and afforestation, since it takes a long time for the planting of trees to actually get used to their environment and taking in a lot of CO2 from the air. That's it.
Okay, hi, my name's Kristen, and I'm going to be discussing the restoration of wetlands as a carbon capture method, and will this work considering today's issues? For a little background, I'm just going to explain what wetlands are. They're areas where water cover the soil or near the surface of the soil for the entire year or seasonally throughout the year. They support both aquatic and terrestrial species. And it's a very unique ecosystem because of the prolonged presence of water on top of the soil. So they favor growth of specially adapted plants called hydrophytes. There are two general categories of wetlands. First, coastal or tidal wetlands, or inland or non-tidal wetlands. Coastal and tidal wetlands must be on an oceanic coast, obviously, and they're very closely related to estuaries. The salt water and the fluctuating level of the water because of the tides create a very difficult environment for plants to live, but some plants like grasses and mangrove trees thrive in this environment. And going on to inland or non-tidal wetlands, most of them are seasonal depending on precipitation and the level of groundwater. And inland wetlands are most common on the floodplains along rivers and streams, shores of lakes and ponds, and low-lying areas with a high water table or heavy precipitation for the whole year or parts of the year. And wetlands are found on every single continent except for Antarctica. And then here's just a very pretty picture of an example of a wetland. There's many functions of wetlands. They're among the most productive ecosystem in the world, and they're comparable to rainforest and coral reefs. Because of the huge amount of biodiversity in wetlands, they're the home to very complex food webs, and many species of birds and mammals rely on wetlands for water, food, shelter, and especially during like migration seasons, birds come back to the same wetlands over and over again for migration and breeding. The microbes in wetlands and plants and wildlife are part of the global cycles for water, nitrogen, and sulfur. And marshes recharge the groundwater supplies and moderate stream flow by providing water to streams. And so they're an important part of the water cycle and water transportation. And they also help reduce damage caused by floods by slowing and storing flood water, because it kind of gets trapped in this like shallow, large area. And also, as the water moves slowly through the marsh, sediment and other pollutants can get caught up in like all of the vegetation and organic material, or they can settle down to the bottom. And marsh vegetation and microorganisms can also use extra nutrients for growth that would otherwise pollute the surface water, like nitrogen and phosphorus from fertilizer, which can cause algal blooms. But the most important function for us today is that wetlands can store carbon within their plants and soil instead of releasing it to the atmosphere as carbon dioxide. So wetlands can actually help moderate the global climate conditions. So here's a global map of just where wetlands are and what type they are. They're basically all around the world, like I said before, and they're like a very common ecosystem. And basically here's another map that just kind of shows in a little bit different way. So wetland as a method for carbon sequestration. All wetlands sequester carbon from the atmosphere through plant photosynthesis and the trapping of sediment runoff. Carbon is held in the living vegetation as well as the peats, the organic soil, and the sediments that have built up sometimes for over thousands of years. And the reason why wetlands are so good at trapping carbon is because the soil is anoxic or oxygen poor. And so the decomposition of organic material is very slow. And so it leads to the accumulation of organic matter in layers, and it doesn't release the carbon into the atmosphere. So just some facts about this is that the US Global Change Research Program estimated that wetlands in the US alone store 13.5 billion metric tons of carbon, and wetlands contain a disproportionate amount of the Earth's total soil carbon, 20 to 30% of the 1,500 pg of global soil carbon, despite only occupying 5 to 8% of its land surface. So wetlands don't have to be very big to have like a huge impact on like the amount of carbon they can store. And wetlands can hold up to 40% of soil carbon compared to agricultural soils, which can only hold 0.5 to 2% of soil carbon. However, wetlands can also release carbon both through natural seasonal changes, through like decomposition in the fall, or when there's like human disruption, the equilibrium can be thrown off and more carbon can be released. So here's a diagram kind of showing the cycle of carbon sequestration in wetlands. Trees and vegetation take up the carbon through photosynthesis, and when the vegetation dies, it sinks below the water into like the peatland. And because it is so anoxic, it doesn't decompose like I was saying before, so it gets trapped there. And on the other side, more like on the left side, it shows what can happen when like the soil is disturbed and it can like release carbon back into the atmosphere. So wetland loss is a huge issue happening globally right now. Unfortunately, many wetland ecosystems have suffered major acreage losses because of human development. Some wetlands have been degraded because excessive deposits of nutrients and sediment from construction and farming. Coastal development leads to the filling in of tidal wetlands, and development can lead to the can lead to diversion of stream flow. And wetlands are being converted to agricultural areas to keep up with food demand. And that goes hand in hand with water drainage because they're draining wetlands to use water for agriculture. And a little statistic is that 35% of the world's wetlands were lost between 1970 and 2015, and the loss rate is accelerating annually since 2000, and they're disappearing 3 times faster than forests. So wetlands aren't in a great place right now globally. But there are some restoration efforts, some of them being just to stop or reduce wetland drainage for agriculture, to control fires in wetlands, especially after a drought, to allow the natural revegetation to occur in wetlands, or to go in and restore like the natural diversity of the vegetation to prevent the takeover of invasive species because of climate change, to stop and control peat harvesting and other practices that disturb or remove carbon from wetlands, promote re-wetting because wetter wetlands take up more carbon than dry ones, and obviously protect wetlands from residential and agriculture development, and use precision agriculture to reduce fertilizer runoff. And here's a picture of successful wetland restoration. So the connection between wetlands and sea level rise, as you've probably heard in a lot of your classes about sea level rise, and there's predicted to be a 2.5 foot sea level rise on the low prediction for 2050. And if this does happen, the sea level will overwhelm many coastal wetlands, and there's no room for them to retreat inland because of coastal development. Wetlands are especially vulnerable to sea level rise because they're already facing so many issues that I just talked about because of human disturbance. And a 1 meter rise in sea level may lead to a 68% loss of the present coastal wetlands. So this diagram kind of shows that I was talking about how if the sea level rises, there's nowhere for these wetlands to retreat inland because there is development and then forests. So will it work? Can restoring wetlands increase carbon sequestration? After doing my research, I think the answer is yes. Wetlands are particularly good at capturing carbon despite covering less land area than other ecosystems like forests. And the USDA reports that the effect of restoring grass wetlands will lead to carbon sequestration. And according to a research article by Restore America's Estuaries, restoring tidal wetlands could lower the greenhouse gases of our atmosphere and offset the impacts of climate change. As a more specific example, research conducted in Washington's Puget Sound area shown that the 3,300 plus acres of wetlands that are planned or under construction currently would help remove at least 2.55 million tons of carbon dioxide from the atmosphere in the next century, which is equal to the annual emissions of 500,000 average sized cars. And so I also want to talk about wetland restoration, increasing carbon sequestration despite sea level rise. Out of my research, I think even though the sea level is rising, wetland restoration will increase carbon capture and is like a thing to worth putting our time into, because freshwater inland wetlands hold nearly 10 times more carbon than tidal coastal wetlands. And inland wetlands aren't threatened by sea level rise. So they're doing a better job at trapping carbon and they're not facing this issue. Specifically in the US, the peatlands and forested regions in the cooler areas of the United States, like the upper Midwest, store the most carbon. So I think going forward, we should restore wetlands to be optimal for carbon capture. So focus our efforts on deep organic soil wetlands and that are very old and that are in more cooler temperatures because they're optimal for capturing carbon. And I think if even the increase of carbon capture cannot be proved at this time, I think wetland restoration is super important just as a preventative method, because the loss of wetlands doesn't just mean like a loss of carbon sequestration, but also means a huge release of all that stored carbon. And we don't really need any more extra carbon in our atmosphere right now. So here are all our sources. Thank you.